Good morning, everybody. So I'm Chris Swan, CTO at Cohesive Networks. Spent about 15 years of my life working in financial services, and before that, the military. So I've dabbled around with security a fair bit over the years. I sometimes talk about security as being the Hotel California of IT. So I occasionally check out, but it always gets me back eventually. If you've got questions, then please use the, don't do that, use the application to ask them, and hopefully Adrian will be keeping an eye on those so that we can answer the questions at the end of the session. So I wanted to start out with this sort of news flash from earlier on in the year. The big news was that Google was saying it was going to move all of its corporate apps onto the internet. And if you get into the detail, that's not quite exactly what they were doing. But the point was, Google had kind of looked at the whole concept of having an intranet or an internal network and said, this just isn't working for us anymore. That we're just as capable of securing applications that are public-facing and that are hosted on the internet, and in their case, hosted on their own cloud platform in their data centers, as we are applications that we consider right now are kind of on this different thing that we call our internal network. And so they're going through this process of saying there's no such thing as the internal network anymore. It is all just going to be applications hosted on our platform that we selectively choose to open up, whether those are accessible to just Google employees or just Google users or just the whole of the world. So I want to set the scene a little bit in terms of what I'm talking about here. So I'm going to start out with a traditional kind of application architecture here. So if we look at a typical application, and I see our customers just with thousands of applications like these, they're generally, a business application is a collection of servers. And because we do stuff on the cloud, we normally see virtual servers. And so you'll have a bunch of servers at the front end doing web tier and sort of typical N-tier architecture, and another bunch of servers in the middle doing the application tier, and another bunch of servers doing the database. And they kind of, I've squeezed those together on the diagram because people are normally doing some sort of clustering stuff, or they're using bigger servers for their database. So they're different from the other servers. And then maybe some message queues off to the side if you've got some asynchronous stuff going on there. And this sort of ends up raising the question of what is the right traffic that should be going between all of these things? And we've answered that question quite often in the wrong way by just saying, oh, it's all behind the firewall, and it doesn't matter what the right traffic is. Any traffic's allowed to move across our network because it's the internal network, and we're safe and happy with that, and it's secure. Now, at some point in the last few weeks, somebody changed the title on the GOTO website and said something about microservices. And I never really planned to talk about microservices, but I'll take that diversion. I would say, in many ways, modern architectures don't actually change very much of these aspects, especially when we're thinking about stuff in terms of network traffic. So if I look at a microservices-based application, rather than being a collection of servers, it's a collection of services. And I might name them different things, so I might call it the persistence services rather than the database tier. But it kind of ends up still being the same diagram, and we still end up asking the same question of what is the right traffic going from one thing to another. Now, I think the key difference here is if we look at exemplars of microservices architectures, and we've got Adrian here in the room who will talk at great length about what went on at Netflix. The way that they ended up building these things dictated a different approach to network architecture and hence a different approach to network security. So if we take something like the persistent services, those persistent services never had a life on Netflix's corporate intranet. They only ever had a life on Amazon EC2 in the context of the virtual private clouds and the security groups that existed there. And so it's ridiculous that those services would have ever been opened up to anything other than the intended traffic. So the whole sort of premise of a cloud security architecture where we're whitelisting things rather than an enterprise network architecture where we're kind of saying good guys inside, bad guys outside, the firewall protects us, is entirely different. And really, it's that change in premise that I want to spend a good chunk of this talk exploring, and the very rapid evolution that we've had over the course of less than a decade in the approaches that we take to doing security, and particularly security at a network level. And I'll explore why we do security at a network level and what's good about that and what can be bad about that. So if we look at an enterprise data center, I a moment ago kind of said, well, here's a typical enterprise application. If we look at an enterprise data center, then it's just X by X of typical applications. Lots and lots of them. And if we look at the spending that happens on security, then 80% of that security spend goes on the perimeter, and about 20% of that goes on all of the rest of the stuff on the interior, things like identity management, the directories that go along with that, data leakage prevention, and so forth. So there's a huge sort of misbalance there. And I think this was touched upon in the introduction to the rugged track by a number of the speakers in terms of we're spending our money in the wrong place. And so the hard on the outside, soft on the inside model has consequences. So when we have a breach, and I think to a certain extent, breaches are inevitable, and a big part of rugged is being able to recover from the inevitable breach in a sort of sane manner. Then with this network security model, one penetration then becomes the stepping stone to the sort of east-west traversal. And I'm not going to name and shame, but I'm sure everybody in the room can think of countless examples over the last year even of organizations where an application has been penetrated, and then they've got into the email, they've got into the CRM, they've got into the crucial business applications, and they've taken all of that sensitive data and posted it onto Pastebin. And it's very embarrassing, and everybody keeps saying something must be done about this. What should be done about it? So cloud architectures, as I kind of already mentioned with the Netflix example, cloud architectures have been different. And they've evolved very quickly. And I want to take a quick journey through that evolution to kind of describe where we've got to. So 2006, Amazon Web Services, which had existed already by that time for about a year, they launched this thing called Elastic Compute Cloud. So Amazon Web Services went from being an actual web service where you could do a SOAP request or an HTTP request, and you could ask about a book, and it would return some data based upon a unique identifier, and you could do different searches and stuff. They had this thing where you could now have coin-operated VMs on demand. So 10 cents an hour bought you an M1 small. And the network security model for that was that every single one of those VMs sat kind of lonely and proud out on the internet. And the only thing that stood between that virtual machine and the big bad internet was a set of Zen security groups in the hypervisor for that. And that turned out to be actually enough to do some really useful stuff. So the Zen security groups were tough enough. We didn't have countless examples of people just kind of busting straight through them and taking over virtual machines. There were lots of security issues with EC2 of that day. Most of them actually revolved around sort of key management and stuff being left behind on storage and all that kind of thing. So the firewall stood up. But a single VM was kind of difficult to work with as soon as you were trying to build applications out of that. So if we go a couple of years on and people were starting to try and do bigger, better, more adventurous things with Amazon, then we saw the arrival of overlay networks. So you'd get one of those VMs and you'd say, you're my special VM that's creating me a network. And then you'd sort of plumb all of the rest of the VMs into that using encrypted network connections. And it ends up forming this kind of conceptual thing where you've got a single network virtualized across the cloud, so that all of those VMs can talk to each other, make a functional application out of many VMs, and also secure the data in motion. So as these VMs are talking to each other, nothing's going around over the public internet. There's not, at this point, a cloud network concept, really. Everything's going over the public internet. It's not going over the public internet in plain text. The VM that's kind of standing at the front of that starts looking like a bastion host. So a concept that we've had from demilitarized zones and sort of layered network security models in the enterprise sort of immediately gets plumbed in there. So 2009, Amazon got to the point where they were like, okay, actually something does need to be done about how we do networking in the cloud. And they introduced this concept of virtual private clouds. And virtual private clouds, there's a whole good number of reasons why they came along. The joke at the time was that Amazon was running out of 10.0.0.0/8 address space in US East. And that actually wasn't true at the time. So there were 16 million IP addresses in that network range. And AWS, even in US East, was nowhere as big as that then. Debatable on whether it's even crossed that line now, but it's certainly got a whole lot bigger since then. But the idea of a virtual private cloud was that it would provide containment, that you could have virtual machines inside of Amazon's network within a contained private network where you had control over the addressing. One of the drawbacks with virtual private cloud is it sort of exposes Amazon's fault design just a little bit too intentionally in your face. So VPCs have to match to an Amazon region. When you make a VPC, it has to be in a region. And VPCs force you to have subnets, and subnets have to be aligned with availability zones. So that fault boundary that you have with availability zones and regions is kind of right there in your face in your network design. And if we look at how some of the other clouds are now doing network architecture, yeah, it's become one of those things where it's a graceless aspect of using Amazon is the fact that you're confronting those fault boundaries so much with your network design. So people started putting their VMs into VPCs, and you now had containment of traffic, and you now had the capability as well to connect between VPCs and enterprise networks using VPN gateways and stuff like that. But containment often wasn't enough. So you still had traffic going around in plain text on the cloud service provider's network. And so to that extent, the overlays hang around because people still wanted to have the encryption of the data in motion, and that gave a reason for the overlays to stay. So lots of people did something like this. They'd take their application and they'd put it inside of a VPC, and then they'd put an overlay over the top of it to secure all of their traffic. And they'd maybe have the overlay network manager at the edge of that providing connectivity into different places, or sometimes acting as that bastion host. Some even did this. So this is a typical example of a fault-tolerant design. So you've got a bunch of VMs in different availability zones, different VPC subnets. And now, if you've got a single outage, then the Amazon fault boundaries should save you. If you were really large and as paranoid as Adrian is, then you'd start doing something like this. So you're not going to just rely on availability zones, and you maybe want to have regional dispersal anyway in order to serve different customers in different places of the world with lower latency. So you start to replicate that cloud architecture across multiple regions. You can even do this as well. So you can, if you want to take the overlay network and stretch it across multiple clouds, whether that's different regions or even different cloud service providers. The good news was that, thankfully, almost nobody was stupid enough to do this, which is to take VPCs and recreate the intranet in the cloud, because that's a bad idea. Intranets, I think, if we go back, were probably a bad idea in the first place. They're just an accident of history. And so as people have been moving workload into the cloud, lots of people have looked at that as an opportunity to not repeat the mistakes of the past. So I'm going to take a quick detour into the worlds of unified threat management and application delivery controller and hopefully answer the question of what is a perimeter actually made of these days. So initially, perimeters were just firewalls. So people would go and buy a firewall, put it in front of part of their network, and that was it. That would keep the bad guys out. And firewalls turn out to be actually pretty lousy at keeping bad guys out. And particularly when we reached a point in time in history where we weren't connecting together things with lots and lots of magical new, pure sockets-based protocols, but in fact, everything was coming in and out over HTTP or HTTPS or a handful of other well-known protocols. And what happens there is the firewall becomes kind of useless because you're saying to the firewall, to do your job, you've got to let HTTP through, and all of this stuff's gushing past on HTTP, and you really don't know whether it's HTTP that's good or HTTP that's bad. So that's why you then start having things like network intrusion detection systems and network intrusion prevention systems, NIDS and NIPS, where you say, okay, let's look at this traffic flying by and do some analysis of it and try and look for signatures of things that we know are bad. But you've also got antivirus gets thrown into that mix. So let's look for some antivirus signatures. Neither of these things work, by the way, because signature-based is always just looking in the rear view mirror. And it can actually be quite damaging because you end up not relying just on signatures. You get some heuristics in there as well, but the heuristics get triggered off by good traffic as well as bad traffic, and now you've got a ton of false positives to deal with. And then you get specific things like anti-spam come along as part of your sort of email perimeter. And then people want to have remote office connectivity, so VPN devices arrive. Data leakage prevention is sort of spotting not bad stuff coming in, but good stuff leaking out. Much of the same technology, much of the same drawbacks. And then things like load balancers were just there to help as part of the network. You try and do load balancing as early as possible. And these were all individual boxes. And they were expensive things, and they had to have very specialized people to own and manage them. And what happened over the course of the last decade was people like Fortinet came along and said, let's just tip all of these different functions into one box, and we'll call that unified threat management. And it'll be much cheaper to just buy one box. And it'll be much cheaper to manage because you only need one specialist in that box to look after all of these different functions. So that was kind of nice. And then if we think about the applications that we're presenting out to the world, we had a whole bunch of networky things that we wanted to do with those. So again, the load balancer comes into that picture. We might want to do some content caching. SSL was slow 15 years ago. People still kind of go on about SSL being slow. It's not anymore. And so Eleanor just showed you how trivial the code is for doing SSL nowadays. And when you look at the impact that that has on a modern CPU, it will hardly notice. But for a little while, SSL had been slow enough that people bought special boxes to do TLS offload. Compression can be useful on that edge. Web application firewalls. We touched on these earlier in the week as well. So the idea that there's bad types of request and that we can get in the way of those and then filter those out. And it's one of those things that looks very elegant, and if you get an open source WAF, you can sort of just get a OWASP rule set and drop it on there, and it'll immediately sort of protect you from all of the OWASP bad things. And then you'll find that your application isn't working like you thought it was going to because you were relying upon bad things. And at that point, you've got a choice. You can either fix your application, which is hard, or you can go and fix the WAF rule set, which is also hard. So it's a bit of a Hobson's choice at that point. Multiplexing and traffic shaping sort of go into the mix there as well. And these things were all standalone boxes for a little while, and they went through the same process that happened with UTM, so they all got squeezed into one thing, and a different company like F5 would sell you a thing called an application delivery controller. And this has been the delivery model for UTM and ADC. So somebody sells you a metal box, and you go and rack and stack it in a data center, and the traffic flows through the box. And the problem with that model is these things become choke points. So you then have to fixate on performance, because this choke point is the thing that's mediating all of the traffic in and out of your network. So it has to scream along at like 10 gigs or even 40 gigs these days to be able to cope with all of that. And if we look at it from a rule set perspective, it has to have the kitchen sink of rules, because it needs to deal with every conceivable piece of infrastructure and applications and supporting components that live beyond that choke point. So it's quite a constraint. But the world is turning. So we now have these fancy new things of software-defined networking and network function virtualization. And I'll try to explain, hopefully, the difference, but there is, in fact, huge overlap between these things. So I see software-defined networking as the ability to configure networks through APIs, so configure networks through things that are software. And network function virtualization as the ability to make networks out of software. And of course, there has to be a huge overlap there, because who in their right minds today would make a network out of software and then have a command line interface in front of it that needed to have a human operator? You would put an API on that, wouldn't you? So that's why we get SDN and NFV coming together. So when we're doing this, what it means is I can take a whole bunch of networking functions, switch, router, firewall, VPN, that kind of stuff, and I can just place them onto a virtual machine. I can go further than that as well. So we've got containers now. I could take a whole bunch of other network functions. I can take my NIDs and NIPs and load balancer and cache and TLS offload and even a WAF. I can throw those into containers. I can throw all of those containers onto my virtual machine that had the core networking functions. And I've now got a networking virtual appliance. And I can take that networking virtual appliance and I can deploy it alongside of my virtual machines that are doing my application and make myself an application-centric perimeter. And this kind of looks and feels pretty much like my old perimeter, but it's different in sort of character and nature. So I'm making lots of these things, which gives me lots of things to manage, but that shouldn't be a problem, because that's why we've got APIs, that's why we've got orchestration at scale. But I can be much more fine-grained now about what all of these things do. So I don't have my kitchen sink problem anymore. I don't have to have a rule set that's dealing with every conceivable application, every conceivable piece of infrastructure that's running on it, with lots of conflicts, because the traffic going into one thing might look bad for another application. I can just focus on that app, its data, and the risks that go along with that. And that allows a different concept around thinking about how I do rules, how I do blacklists and whitelists and things like that. The other piece of it is it does not need to be necessarily screaming fast, because I'm only dealing with the traffic for that app. So although I've gone and made this thing out of virtual machines, and virtual machines aren't doing 10 gigabits line speed networking functions, they don't necessarily need to, because I'm not trying to run an entire enterprise behind this, just one app. And this stuff refactors pretty well into microservices. So as we're building a microservices architecture, I can take those networking functions and either embed them into my microservices as I'm creating them, or I can deploy them alongside of my microservices. So the networking functions are just different services in my microservices architecture. So they're just building out a richness to that microservices deployment. So I want to touch upon a thing now that I've been talking about for a little while now that I call the audit paradox, and explain some of the mess that we found ourselves in. So when we talk about security, you talk to any security expert, they'll tell you it's better to build in security at the beginning than it is to bolt it on later on. So just like this elegant piece of brickwork here, you should build the security right into your code. That's the good thing to do. And so what does that look like? It looks hard. So here is a screenshot of a tiny fraction of actually the Microsoft Developer Network guidance for API security of web services. This is like one part of one page of like 64 pages or something. And getting a developer to follow that guidance in the first place is a tricky process. But the audit paradox comes about because even if the developer has gone through all 64 pages of that stuff and done it all completely correctly, how can you tell? And then when you're making changes to the code, how can you tell that you've not inadvertently gone along and broken one of those rules? You know, you got somebody new onto the team, they weren't quite up to speed with what they were supposed to do, they made that one-line change, and now how do you know that that didn't break what you were trying to do? Which is why we've had so much bolting on of security. Because if we look at the mechanism for what does bolting on look like looks like exactly those UTMs and ADCs that we had before. And you know what auditors like about these? It's a standalone thing. They can go along to this and have a look at its configuration and say, yeah, I'm happy with that. You know, I watched that configuration take shape. I saw that there was a change management process that arrived at that configuration. I've got an external view of what's going in and out. And I think that's why we've ended up in the situation where so many of our security controls have been bolted on rather than built in, because of this thing that I'm now calling the audit paradox, that it's easier to audit security controls that are standalone than it is to audit security controls that are built in. Platforms, I think, give us an opportunity to have a bit of best of both worlds. So if we look at what we can get out of platform as a service, then that gives us a chance to bolt in. So the maker of the platform as a service can take that 64 pages of security guidance for doing web service APIs, and they can make that part of the framework. And that can be audited the hard way, but it needs to be just done once, because the developer writing code on top of that framework has had that done for them, and they're just concentrating on their application functionality, and you've sort of got that independent verification piece and the auditability of it. And if you kind of go to Alexis's talk yesterday, then the problem is nobody wants, not nobody, a less large community wants to have an opinion, right, yeah, many developers do not want opinionated platforms as a service. Docker has set people free, or containers in general have given people the ability to take whatever it was that they like and package it up and move it around. So the popularity of Docker, for me, shows that there is a distinct movement against opinionated platforms, which kind of drives us against having bolting in of security. I also just wanted to touch upon monitoring. If a security event happens that doesn't go into a monitoring system, then I would contend that it might as well not have had a security control in the first place. So I've seen situations where the best case for a security control was that it was going to tell you what bad thing happened after it became obvious by some other means when you went back and looked. And that's really not very much good at all. So, an hour or so ago, Elno was up here saying, be nasty to your logs and have people pick their way through them. And just make sure that there are logs. Make sure it is being funneled into a processing system that makes it human reactable, and that there is actually a human taking reactions, and put the test cases through to do that. So some challenges remain on this. If we think about a concept of sec DevOps, and I think that's kind of where we've been driving over the last few days, is to say, not just let's have DevOps, but let's do DevOps securely and have secure DevOps. then it falls out to this. This is my sort of to-do list of Sec DevOps. So APIs, I think, are necessary but not sufficient. So I've talked about being able to do network security with virtual machines and software-defined networking, and that the ability of us to have APIs allows us to do that. So we can take network operations, and we can take things that were difficult and expensive because we bought boxes and we had them managed by people on the end of command lines, and we can turn those into virtual machines that are managed by orchestration systems. And that completely changes the game, because my change to the network now isn't a ticket into the NOC that takes them a week to reject for some flimsy reason, and then I have to redo it again. My change to the networking environment is part of my push to production. So, hey, there was some config in there. It went into the orchestration system. The orchestration reconfigured my virtualized network for me, and off I go. So the point is, it needs to be integrated into the overall system. So our APIs give us the starting point, but APIs are only useful when they are integrated. The second point is about control metadata. So I have to have visibility and understandability of my control metadata. This is the stuff that the auditors end up wanting to have a look at. I should also ask about how mutable my control metadata is as well. So what are the mechanisms that make changes to control metadata, and what control do I have over those? So at a kind of point level, the auditor needs to be able to come along and inspect the config of something and decide whether it's right. At a management level, the auditor needs to have confidence over the control flows that create that config in the first place. And I think this is an area where there's definitely more work needs to be done. So I was talking a little while ago about the attraction of, we can have a different rule set for every application, and that's great. And we can go all the way back to the business there and say, what are the things that keeps you awake at night about how your data might be exploited if an attacker gets at it? And they can tell us, and we can design rules to help defend against that. But that's a very large distributed processing human task to collect that in the first place, to build the threat models, to build out the rule sets, and then to have control over getting those rule sets into production and have confidence that we've got the right rule sets in production and that we're responding appropriately to messages that come out of the system when it's seeing things that flow by that are tickling those rules. And then lastly, those security events do need to be captured, and they need to be turned into ultimately something that humans can take action on. So a lot of security monitoring systems are dealing with a flood of false positives. One of the reasons for the flood of false positives that we cope with at the moment is these choke points and the fact that we have these kitchen sinks of rules in those. So we can tune our way out of the flood of false positives to a certain extent by having more discrete rule sets for our given applications or our given services. But it's still not going to be perfect. So we're still going to have a fire hose of security event monitoring data, and we still need to be able to determine whether something coming out of that fire hose is actually an actionable attack or an actionable compromise of a system where something needs to be done. Worst case, you're actually going to take yourself offline because remaining online is worse for your business than stopping, going back and fixing what's going on. So that's the to-do list. And I think what I wanted to kind of conclude with here is the call to action for us to get to Sec DevOps is to work on that to-do list. So to make APIs for security controls, but furthermore to make those APIs integrated into an overall system, to have the control metadata and the visibility over it, and to have actionable security events ultimately emitting out of our systems that humans can take the right action on. So, thank you very much for listening. Please, as ever, remember to rate the session. And I've finished pretty much on time, so happy to answer any questions. Yes, Adrian.
So you were talking about developing threat models for customers specific to their needs, but aren't most threats pretty similar across customers?
So if you look at this threat modeling exercise, and I think the people that have kind of best popularized this have been Microsoft with their secure development lifecycle. And there's a lot of things that I could dislike about SSDLC because it's somewhat still tied to an old waterfall model. But the threat model consists of sort of two key aspects at the beginning as you're sort of thinking about your application. So it asks you to think about the data that you're managing, and it asks you to think about the roles of the people interacting with that data. And those two things are unique to every single different application.
So you do like classifying exactly which things labels again.
Yeah. So what you then get into is, who are the bad guys that would be wanting to go after this data? That has less variability in it now. So, if you look at some of the stuff that Schneier says about, you've got this spectrum of attackers, and he now goes kind of two cell matrix on it. It's kind of, you've got the unintentional and the intentional attackers. So the intentional attackers are just coming after you for the thing that you have that they value. And on the other side, it's kind of, they don't care, they're just going to attack somebody. And then you've kind of got that level of sophistication thing of, Josh sometimes talks about H.D. Moore's law of you need to be able to protect against today's version of the scripting kits. And actually, compliance tends to move much slower than that. So the scripting kits are evolving day by day by day. And the most basic script kiddie can just go along and pull those from Git and have a go at you. And like at the top end of the scale is probably something like Stuxnet. Though one of the problems with Stuxnet is once it got out there into the wild, it provided a toolkit for anybody else to build a Stuxnet, which was kind of super unhelpful. So you've got that sophistication and attackability matrix to think about. And then, if we think about how that then maps into vulnerabilities, that's just a question of which software are you using and what aspects of vulnerability does it potentially have. So that comes from your stack. And you're going to make architectural choices in how you implement the software, which leads to a stack, which leads to a set of pre-existing vulnerabilities in some cases. And Josh spent a lot of time saying there's so much stuff that's kind of known about, and some of it's patched and some of it's not. And of course, you should be trying to be on the patched stuff. But you might not actually have choices sometimes. You might have known vulnerabilities in your code. And you have to, that's why we have mitigating controls. So a lot of security controls are put in there specifically for the purpose of dealing with the known vulnerabilities elsewhere in the system to try and prevent them from being attacked. And as noted in Nick's presentation this morning, a lot of the time the vulnerabilities are in the security software itself. So your controls just introducing extra complexity and more things that go wrong.
You mentioned that sort of idea of developers don't want opinionated platforms. Is the answer to change that mindset? And if so, how? Or is the answer to come up with unopinionated platforms or unopinionated tools that lead us in the same direction?
I think this actually comes from a sort of spectrum of skill and trust. If I look at the organizations that seem to be keen on opinionated platforms, it's organizations that don't have much trust in their developers because they consider them to be of lower skill. And that can come about because they're hiring kids straight out of college, or they're outsourcing development to places where they aren't actually paying for highly skilled developers. And so opinionated platforms look attractive to those types of organizations because they're kind of constraining the adventure space. And they're constraining the need to develop skills in order to be productive. I think where we look at more high trust, high skill environments, then people feel more confident allowing their developers to go off and do whatever it is that they think is best because the trust is there. So this kind of trade-off between opinionated platforms and less opinionated approaches, let's call them, becomes one that at its heart is about trust and skill level of the developer. Now, if we're saying there's a security trade-off there because we can bolt security into the opinionated platform, but we rely on the developer to build security themselves into the less opinionated approach, then we answer our own question there by saying the higher skilled, more trusted developer should actually be capable of building the security in when they're doing that.
There's different, with a sort of more disaggregated platform, you just have different security tooling. It's enforced in a different way.
Yeah,
Right?
and that's
so every service that gets launched at Netflix gets penetration tested with every new version automatically. So it's like trust but verify, rather than put you in a straitjacket up front. So we let you do whatever you want. If you do something stupid, we'll notice that and we'll shut you down or we'll point.
The other side of the skill thing, though, is there's a group of people, like, you take all the people who are in that bucket who don't want the other units. Some of those are very skilled and some of them are copying the people who are skilled.
yeah, you're going to have cowboys.
And do we just have to write off basically like 90% of that 50%, or is there something better?
So, to a certain extent, this only matters in the face of success. So if you've got cowboy hacks together, something following in the footsteps of more skilled people, that then they're able to copy the pattern and maybe even cut and paste some of the code, but they're not really understanding what they're doing and they're introducing vulnerabilities. It only matters in the face of success where people start really using that service and they start putting sensitive data into it, or it becomes financially important. And the good thing about success in that context is it tends to bring in more resources and it tends to bring in more skill, which can be used to deal with the outcomes of that. So I think if we look at these things as kind of ecosystems that have feedback loops within it, you end up with the feedback loops being built to correct some of those problems that might take place early on in the development of something. And again, when Adrian's talking about the evolution of Netflix, it is an evolutionary story. They started out with a monolith, and it changed into this, and then it changed into this other thing, and then it kept on changing. And the security story that's buried within that is, I think, equally fascinating. That actually they began being pretty good at security, but they got better and better and better, and security became a part of the chaos monkey. There's a security monkey, isn't there, as part of the simian army. So these automated tools came along as part of professionalizing an approach to security. Now, that gives a template for other organizations that are taking a journey that might have a similar destination to Netflix to look at and to try to emulate. But I think you can be iterative and you can rely upon feedback loops to be corrective here. I think a lot of the problems come along where actually you've got organizations that have got a portfolio of stuff and you've just got some really bad things within that portfolio. And especially with the one perimeter around them all model, it's kind of they then become the weak spots that make the other things more vulnerable than they ought to have been. Saw a question at the back.
Yeah, well, I was just thinking, with the reduction in false positives watching the internal network, is there any evidence that this approach allowing you to pick up APTs quicker than you normally would?
I'd say it's far too early days for that. And also, I'd kind of return to a point that's been stressed a lot over the past couple of days, which is most attacks aren't APTs. Most attacks are relatively unsophisticated and usually taking advantage of known vulnerabilities that have been in existence for years, if not decades. So this makes APTs actually somewhat mythical beasts. Let's take a look at maybe something like the RSA attack. That's interesting because that actually really was an APT, and there's a certain amount now of public on-the-record examination of how exactly that went down in the first place, how they didn't notice it for most of the duration of the attack going on, and how they did eventually see it with a new networking monitoring tool that they ended up trying out and acquiring because that just happened to be there in the right place at the right time. And part of the sort of codicil of that story is if they'd not been planning that potential acquisition, they'd have probably never even noticed. And so, whilst you've got a whole ton of false positives, and whilst you've got an occasional piece of forensic evidence about an APT, there's a sort of unknown unknowns piece to that, where there's probably not that many APTs actually going on because of the degree of sophistication involved to do them and the cost that goes along with that. But if they're successful APTs, you're not even detecting them. So we don't actually have much in the way of data to go on of what does the comparative position look like when you start squeezing out a lot of the false positives.
There's an interesting problem here, which is that if we assume that most companies have been compromised at some level, and you're trying to sell a product that detects that a company has been compromised, and the CISO is trying to buy this, but is probably going to get fired when you run the tool. So there's a kind of a little problem in the sales process that the team that runs the tool discovers that they've been breached for the last 6 months and all their data's been sent to China or whatever, right? There's been a few cases where a very unwelcome part of product being kicked out because it worked. Right, so you have to figure out how to get through that part of the sales process. So it's actually interesting times for selling that class of product.
And my friend Ian Griggs did a brilliant paper about this in about 2008, where he described the security market as a market for silver bullets. And it was all about information asymmetry. So if we think about kind of classic markets, then in a perfect market, the buyer knows what they're buying and the seller knows what they're selling, and there's good information about it on both sides, and money changes hands, goods change place. And we can also think about what we term lemon and lime markets. So in a lemon market, like used cars, it's kind of the seller knows that he's clocked it and he's put some bad parts in it and stuff like that, and the buyer is just seeing the car and thinks that it's okay and thinks that it's got an honest mileage on it. And lime markets are sort of the opposite quadrant. It can happen in things like insurance, where I've been feeling a bit ill and I just bought a life insurance policy, and then I go to the doctor and he tells me I've got cancer. And the life insurance company took on that risk where I had some information that they didn't. And Ian said security is a market for silver bullets because neither the buyer nor the seller knows where what they're doing works. And there's an interesting sort of third dimension comes to this, which is quite often the attacker does. So a sophisticated attacker does know which security controls they can breeze straight past, and they're not revealing that information. So a huge chunk of our present security industry is a market for silver bullets because money's changing hands and neither the buyer nor the seller knows whether the goods are effective. And only the attackers do, and they're not saying. Questions on the... Right, let's see. Apologies if you've already addressed the question, major difference in network between traditional three-layer apps and those based on microservices in terms of north-west traffic and whether this entails more east-west and whether there's any implications for security. Again, not a ton of data on this, but if we look at the sort of the destination back to persistence, the whole idea of north-south is we're starting off at a front end, normally a web front end, and we're ending up in a database of some kind, and we might call that a persistence service. And I don't think there's actually anything fundamentally different when you go to a microservices architecture versus sort of more traditional, maybe monolithic architecture. The microservices architectures are generally designed to scale. And so you end up with more east-west traffic where you are doing replication of state. But that tends to actually push the east-west traffic still into the state management layer, if we think about it in those terms. And so you might have gone from having some clustered Oracle instances to having a bunch of Cassandra that's now synchronizing across a region in AWS. But your east-west traffic is still really just within your state management piece. And everything else, sort of top and bottom from it, is going north-south. So I don't think it makes a huge difference.
I mean, if you hit a monolithic app, most of the traffic is inside the app. So the north-south the traffic inside the app is actually east-west traffic, because you're just calling between different microservices. So there's additional just request traffic as your request explodes out into 50 different services, 5 layers deep.
Yeah.
So that's I think where most of the extra traffic comes from. I've seen some people starting to worry about that and trying to figure out that rather than there's so much more traffic that if you want to put some kind of firewall on there, that it needs to look at things in a lot more detail, but it needs to be much more efficient.
Yeah, and I was talking to some AWS engineers the other day about what can be done at line speed and what has to be funneled through VMs. And they're starting to see application architectures break upon what cannot quite be funneled through a VM and needs to be made line speed somewhere else.
Netflix has been having trouble moving to VPC from EC2 Classic because they have some services that need too many entries in their security groups.
Yeah. Question about WAFs. Surely the enforcement of OWASP best practices on applications is good. Yes, absolutely. So you can get the whole sort of OWASP thing canned as a set of WAF rules. My point was, if you've already written your application and tested it, you might find that difficult to live with as a bolt-on afterwards. If you begin your process with those WAF rules in front of it and everything that you ever test lives with those WAF rules, you will end up in a different place and you'll be able to live with them quite easily. The notion of sort of taking UTM and ADC and virtualizing it, doesn't that just spread the complexity? Yes, it absolutely does. In terms of complexity, it makes it horrendously worse. So you're taking what has been, logically at least, a single choke point, which might have physically just been a handful of boxes, and you're potentially exploding that out into thousands of VMs. And the only way that you can cope with that is by moving away from a manual configuration model to basically a DevOps model where you're relying upon infrastructure as code to be able to take care of the configuration of these thousands of things rather than this handful of things, because there's no way you would manage that with the traditional model. So it is kind of what one hand gives, the other takes away, but it does allow progress towards a different model. So that's it on it. Thank you very much, everybody.